Imagine you're an astronaut out drifting in deep space. When you throw a rock as hard as you can, what's going to happen to that rock? Well, you would think that it would continue with constant velocity in a straight line. That's just Newton's first law. But what actually happens is it eventually slows down and stops. So why does this happen? Where did all the rock's energy go? At the turn of the 20th century, the problem of energy conservation baffled some of the greatest minds, including Albert Einstein. Einstein came up with a possible solution. But then, a little-known unpaid mathematician named Emmy Noether proved he was wrong. And in doing so, she created a whole new paradigm for physics, one that underlies all of particle physics and explains why anything is conserved. It all started in 1915 at the University of Göttingen, where Einstein was giving 6 lectures on his new theory of gravity, what would become the general theory of relativity. The lectures were well received, but Einstein hadn't yet settled on the final form of the field equations. One problem he was facing was how to show that total energy was conserved in his new theory.
This is the whole beginning of this story, right? Classically, they thought they had this understanding of what the energy of a gravitational field was. All of a sudden, with these new equations, they go, where is it? Is it in the curvature? Is it in the stress energy tensor? Where's the term that we're looking for?
Einstein suggested that the principle of conservation of energy, long established as a bedrock of physics, might hold the key to working out the correct field equations. In the audience, legendary mathematician David Hilbert was intrigued. So he started to look for the energy conservation equations in Einstein's new theory. But the best he could find was a set of equations known as the Bianchi identities. They showed that energy was conserved, but only in a completely empty universe. So for one like ours, filled with stuff, they seemed useless. Hilbert was stumped.
Fortunately, he knew just the person for the job. His new assistant, Emmy Noether.
From an early age, Noether had dreamed of following in the footsteps of her father, a mathematics professor at the University of Erlangen. She got special permission to attend lectures at the university, but they refused to admit her as an official student. So, in 1903, she spent a semester at Göttingen instead. There, she learned about a new way to approach geometry, using symmetry. Symmetry is one of those ideas that's easy to recognize, but harder to describe.
If I align a mirror on this triangle like so, then it looks the same as without the mirror. And that's because this is an axis of symmetry. Reflections about this axis leave the triangle unchanged. And the same thing happens if I put the mirror like this, or if I orient the mirror like this. So this triangle has 3 axes of symmetry. Now, mathematicians generalize the idea of symmetry further to be any action you can take that leaves an object unchanged. So something else I could do is I could rotate this triangle by 120 degrees, or by 240 degrees, or by 360 degrees. Together, these 6 actions capture all the symmetries of the equilateral triangle.
But you can also have more abstract symmetries. For example, with a mathematical function. If I shift this function up or down by some constant amount, call it a, then all of its y values will change. But if I differentiate that function, I get the slope, and that remains unchanged regardless of whatever constant is added. So you can add any constant to this function, and its derivative always stays the same. So there's a kind of translation symmetry. And unlike the symmetries of the triangle, this is a continuous symmetry, meaning you can shift it by any amount you like. Over the next 12 years, Noether became a leading expert on symmetry. She became only the 2nd woman in Germany to earn a PhD in mathematics, and she used this expertise to help Hilbert and Einstein with their problem of energy conservation. The issue had bothered Einstein so much that he proposed a new conservation equation. It said that if we add together the energy of matter and the energy of the gravitational field, then that total remains constant. Its change over time and space is 0. But when Noether saw this, she was convinced Einstein had made a fundamental mistake, because this equation disregards the foundational principle that general relativity is built on. So Noether knew that Einstein's proposed solution couldn't be the answer, and that made her think. What if general covariance and energy conservation are simply incompatible? And if that's the case, then why? General covariance says that laws of physics must stay the same when you change reference frames. So that is a kind of symmetry, exactly what Noether had spent her career studying. So she started thinking about the symmetries of the universe, beginning with the simplest possible case, an empty, static universe. Imagine you're an astronaut in this universe. Since it's empty, there is nothing special about any particular point. I mean, it doesn't matter if you're over here or over there. The universe is completely symmetric under translations in space. So suppose you throw a ball. Well, it'll travel at a given speed, and after a short amount of time, it will have traveled some distance. But since the laws of physics are the same here as just before, we can shift the whole universe, and we're back to the situation we started with. And we can keep doing this over and over, and this shows us that the object will continue with that same speed indefinitely. So what we've discovered is that the principle of conservation of momentum is a direct result of the fact that there's a translation symmetry in the universe, that an experiment done in one spot will give identical results to that same experiment done somewhere else. You could move everything from one place to another and the physics won't change. Similarly, the laws of physics don't depend on whether you perform an experiment like this or rotate everything by 90 degrees. This universe is symmetric under rotations. So imagine we take a metal rod and spin it. If we let it rotate for a minute, then it will have moved through a small angle. But we can rotate the whole universe back by that same angle, and now we're at the starting position again. And we can keep doing this so that each instant looks exactly the same as the one before, which means the object will keep rotating this way indefinitely. So the law of conservation of angular momentum comes from the rotational symmetry of the universe. Now, another important symmetry of this universe is time symmetry. The laws of physics don't change over time. If you do an experiment today or tomorrow, you will get the same result. So what does this symmetry lead to?
What we've discovered is that time translation symmetry is equivalent to saying that energy is conserved.
The principle of conservation of energy is a direct consequence of time translation symmetry. In a theorem, Noether proved that all of these examples are no coincidence. For centuries, people had no idea where conservation laws came from, but now Noether had discovered the origin of all of them. She proved that anytime you have a continuous symmetry, you get a corresponding conservation law. Translational symmetry gives you conservation of momentum, rotational symmetry gives you conservation of angular momentum, and time translation symmetry gives you conservation of energy. Noether's first theorem explains why a rock or a photon loses energy, but it didn't fully solve the problem of energy conservation in general relativity. See, so far, Noether had only dealt with an empty universe, where you could shift the whole universe and the laws of physics would stay the same. But this doesn't work in general relativity, where the curvature can change from one point to another. Now, if you shift the whole universe, rotate it, or let it evolve in time, things don't stay exactly the same. So you no longer have these global symmetries. But Noether realized there are still other symmetries left. See, no matter how you're moving, the laws of physics always look the same. That's general covariance, and it is a kind of symmetry that holds everywhere. It means that in any small region, we can always change our frame of reference. We can transform the points of space around as much as we like. And since these transformations aren't global, but local, these are called local symmetries. In a second theorem, Noether proved that for these local symmetries, you no longer get proper conservation laws like we're used to in classical physics. Instead, you get something that only works locally, a continuity equation. One example of a continuity equation describes the flow of water through a pipe. This first term tells you how the amount of water changes in a section of the pipe, and the second tells you the difference between how much water is flowing out and how much is flowing in. In this case, the first term is positive because the water level in this pipe section is increasing, and the second term will be negative because less water is flowing out of the section than in. Together, the two terms cancel to give 0, which guarantees that no water is created or destroyed. If the total amount of water changes in a section, there must either be excess water flowing in or out.
In the case of general relativity, Noether found a similar continuity equation, but with an important difference. Imagine that now our pipes are little patches of spacetime, and the water is energy flowing from one patch to another. In any individual section, the continuity equation looks exactly the same as before, so that in any small region of spacetime, energy is conserved. But when we link these sections together, we need to take into account the curvature of spacetime, and this changes the equation. Now it's as if there are little cracks appearing between different sections of pipe, between the local patches of spacetime. And through those cracks, energy can leak out.
In special relativity, the pipe is imperturbable because the pipe is fixed. And in general relativity, we have to account for the energy that goes into other kinds of change over time. And that gets correspondingly more tricky.
Now that we have this new equation, we can see how it works by expanding it as a sum of different terms. This first term is analogous to the continuity equation from before, the one which conserves energy within a local patch of spacetime. But now we have all these extra terms. These describe the curvature of spacetime. So as energy decreases in the first term, these curvature terms increase.
The energy that you lose from the system you're tracking, we now start attributing it to things like the gravitational field, which has changed because the whole universe is stretched. We have to account for the energy that we attribute to the action of the gravitational field as well, because space and time themselves aren't sitting still.
And all of this can be described by the continuity equation Noether had found. But when she looked at it, she realized something. It was exactly equivalent to the Bianchi identities, the half-solution Hilbert had found. He had dismissed it because it only gave you proper energy conservation in an empty universe. But now Noether proved that it was the best you could do in general relativity. With one paper, she had uncovered the source of all conservation laws, and she had solved the problem in general relativity that eluded Hilbert and Einstein.
She was so amazing. I mean, I would go out on a limb and I would say these two theorems are probably the most important theorems for physics of the 20th century.